So here's what we think is what's going on. Okay, so this presynaptic terminal would represent the presynaptic terminal of the CA3 neuron, right? The CA3 axon that would end in an axon terminal. And this dendritic spine of the postsynaptic neuron, this would be what's occurring in CA1, okay, in this Schaefer collateral synapse. And so what we think occurs is that at low frequency stimulation, glutamate is still binding to both receptors. So it's binding both AMPA and NMDA. But what you can see is that magnesium here is still stuck in the pore, because this cell, right, this postsynaptic cell here, is not at all depolarized. Right? It's still at its resting membrane potential, and that means magnesium is still going to stay there. So, but magnesium still blocks the NMDA receptor pore. So this means that the EPSP is generated entirely by AMPA receptors. Right, and so again, what we saw typically is under low frequency stimulations, like in that control cell, there would still be a postsynaptic response, right? And we think that postsynaptic response were sodium ions which come in to the postsynaptic neuron through AMPA receptors. Okay? Now, under high frequency stimulation, so during or immediately after, we think what happens is that this prolonged depolarization is enough to expel the magnesium, right? So we get a prolonged depolarization postsynaptically, right? Again, thanks to AMPA receptors. So if we go to the figure on the right here, you can see this is during a prolonged depolarization. Glutamate still binds to AMPA receptors, and sodium comes in, and this is enough to depolarize this dendrite, okay? And now that this dendrite is depolarized because of the entry of sodium, that pops the magnesium off, okay? So during or after high frequency stimulation, prolonged postsynaptic depolarization allows magnesium ion to be expelled. Okay, so now the magnesium isn't stuck in the pore anymore like it was here. And remember, the glutamate is still bound to the NMDA receptor, right? That wasn't the problem, right? Glutamate is here and here. It was this magnesium that was in the way. But because this is now depolarized, this postsynaptic dendrite is depolarized, magnesium can be gone. And the result of this is that calcium enters. So one thing about NMDA receptors, if you remember, compared to AMPA receptors, is that they were more permeable to calcium. Okay, so calcium increases, the concentration increases. In this specific area, in what we call these dendritic spines. Okay, so let me just take a moment to explain a dendritic spine. I don't think we've used that terminology before, but you know, it's not as if we've got some axon terminal and then the dendrite, right, which is just this long extension, right? So it's not that the dendrite is, you know, like this. Typically what we see with a dendrite is that there are little extensions from them, right, wherever we have a connection between presynaptic terminal, right? So maybe your dendrite would look like this. Right, so you'd have an extension here for this synapse, and then maybe on the other side, right, there may be another terminal that comes in here, right? And so this would be the spine of the dendrite, that extension of the dendrite that makes contact with the presynaptic axon terminal, okay? And so we see calcium increasing in concentration in these dendritic spines here. Okay. So let's talk a little bit more about how calcium triggers changes, okay? So the first thing to mention is that, well, we think that this is what's happening because when calcium chelators are injected onto that postsynaptic CA3 cell, not onto, but into. Did I say CA3? I meant CA1. Because that's the postsynaptic cell, right? The postsynaptic CA1 cell. Remember what a chelator does, right? It sort of sponges up the calcium. And so when calcium chelators are injected, no more LTP. Okay, so again, we think that we have pretty good evidence of this because those calcium chelators eliminate LTP. The question then becomes, what is the calcium doing? And if you remember back to the previous chapter, calcium works oftentimes as a second messenger, right? So we think that the calcium is able to eventually bind to calmodulin and activate CAM kinases. Particularly CAM kinase 2. How do we know that? Well, we've got some imaging studies that would suggest this, right? So in control conditions, right, we see pretty low, right? Blue colors indicate low CAM kinase activity. During stimulation, right, the cell lights up here. This is, so you can see this is probably a spine of a dendrite. And so we're looking at a dendrite here. You can see that the CAM kinase 2 levels go way up. But then 30 seconds after we give that high frequency stimulation, CAM kinase 2 is still on the scene. Okay? And you can see that the changes in CAM kinase during stimulation, right here, right, the levels are going way up. So typically there's not much happening with CAM kinase. But if we think what's happening is calcium is coming into the cell, binding to calmodulin and activating CAM kinase 2, we have some experimental evidence for that, right? Because here's CAM kinase 2 activity going up, and here it is visually going up. Another way that we can show this is by deletion of the gene. So we can knock out the gene for CAMK2. And what do you think happens? No LTP. So even with the paradigm of high-frequency stimulation and everything that we said about calcium increasing in the dendrites, that's not enough to inhibit or to cause LTP when there is no CAM kinase present, right, because we've deleted that gene. So I think we're able to say, right, from these data, that strengthening of synapses is due to increased sensitivity to glutamate. Now, this occurs in two ways, and we've really only talked about one of them, right? So we have to split this idea of strengthening into two different ideas. One is strengthening via induction, that is, we can induce LTP by activating previously unresponsive receptors. All right, so NMDA receptors would be an example of this, right? We can strengthen a synapse by activating receptors, NMDA receptors, that were previously not doing anything. A second way would be via expression or maintenance of proteins at the synapse. So we've discussed this one already, right? That's done. We have to talk about changes in protein expression and maintenance, right? We have to put the long-term and long-term potentiation, and this happens much more in this manner, okay? And so we think that this occurs due to AMPA receptor insertion. That is, at these synapses, more AMPA receptors get inserted, and therefore there'll be a larger response. We can see evidence of this in panel A here, right? So before any LTP was occurring, there was some activity, right? So they're going to stimulate the presynaptic neuron and measure the postsynaptic response, this time colorimetrically. And you do see a little bit of color change, so you do get some current. Looks like there's some current flowing in here. And then they induce LTP. Okay, so then they trigger LTP, and you would expect what you would normally see, right? A larger postsynaptic response. And in this case, after LTP, but not just after LTP, but this is 2 hours after LTP, the strengthened synapse still exists. You can see greater amounts of current that are flowing into this dendrite. Okay? So again, we think that this is due to AMPA receptor insertion because of the time course, right? Because we're on a time course now of 120 minutes, not 5 minutes. So there had to be some change with respect to the proteins, because this wouldn't be this would be too long for that calcium to persist within the dendrite. We think that this strengthened synapse will exist and stay present as long as we maintain stimulation, right? So figure B here, panel B, looks at the glutamate response, percent of control, right? So before we give the high frequency stimulation here, right, we give some control responses that give us 100% of the response. And then immediately, right, we see this large jump. This represents LTP, probably the early phase, right? This would be through NMDA receptors. But as we go out to over an hour, right, calcium isn't going to stay in those dendrites that long. And so we would think that the longer part, right, this would have to be due to AMPA receptor insertion. We're getting tight on time, but I'll mention next time when we come back silent synapses, as well as talk about synaptic depression. All right, there will be a assignment that's posted again on Friday for you to do by Monday. If you have questions about this is not easy stuff, so let me know. We can chat, we can run through the figures, all right? I think I can make this easier for you if you want to do this individually as well.